we've just learned about functions. These things that take some input and produce an output in some kind of predictable way. We've seen that functions can be represented with rules, and they can also be represented with tables. We've also seen that if we have the rule, it's quite easy to produce the table. But what if we have the opposite situation? If we have a table and we want to know what the rule is? Well, doing that in general is actually quite a complicated problem. But we're not going to look at all possible functions. We're going to focus on one of the simplest, but also most important functions there are, the linear function. A linear function is a function whose output results from multiplying the input by a constant and adding another constant. Now this might seem quite limiting. You'll notice it doesn't mention dividing or subtracting. But remember, dividing is just multiplying a reciprocal, and subtracting is just adding a negative. So it kind of does include dividing and subtracting as well. Now, all linear functions can be written in this same general form, which looks like this. Y equals m times x plus b. Now, keep in mind here, m and b are just numbers. In fact, here it states that they're constants. We don't know what they are currently because we're trying to represent this for all functions in general. But m is the number that we multiply by, and b is the number that we add. So we take our input, multiply it by m, and add b, and that is our output. So let's look at some functions, some linear functions specifically, and see if we can identify these two constants, m and b. So for this first one, we're multiplying x by -3, so that's our m, and we're adding 7, so that was b. So that wasn't too difficult. Now sometimes our m and b might be in disguise a little bit. So for this one, x is being divided by 4. But remember, dividing by 4 is the same as multiplying by a quarter. So that's what m is. Also, subtracting 9 is the same as adding -9. So that's our b. For this one, x is being multiplied by 9. So that's our m. And, well, nothing's been added. Well, that's really just the same as adding 0. So we can say that our constant b is 0. For this one, this looks a little unusual because we're actually multiplying the x back here rather than in the first term. Now, once you're used to these, you can figure this out pretty easily just by looking at the function. But let's make it a bit more obvious here by rewriting the order of these two terms. Don't forget, this subtraction belongs to the 7x term, not to the 13. So, this means that m is -7 and b is 13. This one looks a bit unusual because we've got parentheses. But by simply distributing, we can put it into the form that we want. So -4 times x is -4x. And -4 times -5 is +20. So m is -4 and b is 20. For this one, we've got to do some distributing as well, but we're effectively distributing our denominator here. 3 divided by 6 is 1/2. And 4 divided by 6 is 2/3. So now I have my nice linear form. So m equals 1/2 and b equals 2/3. Now there's a particular thing that's really important for us to understand in linear functions. they have something that we call the rate of change. So what this is the ratio of the change in the output and the change in the input. So what it's doing is it's measuring how much does our output y change as the input x changes. And this is how it's defined as an equation. The rate of change is the change in the output, which is y, divided by the change in x. Now, we use these phrases, the change in, very frequently, so we have an abbreviation for it, which we write like this. Now, this is not a triangle, this is the Greek letter delta, so you could pronounce this as delta y divided by delta x. But you can easily say change in y divided by change in x. But that's what this triangle, this delta symbol, means. It means change. Let's have a look at a couple of functions and see if we can work out what their rates of change are. So, for the function y equals 4x take 2, what we can do is we can, for each of our inputs, work out our output. So, for x equals 0, we'll have negative 2, because it will be 0 take 2. 4 times 1 is 4, take 2 is 2. 4 times 2 is 8, take 2 is 6. 4 times 3 is 12, take 2 is 10. And then 4 times 4, take 2 is 14. Now let's look at our changes here. So remember, this is x, so we want to look at how x changes going from number to number. So from 0 to 1, we add 1. From 1 to 2, we add 1, and then we add 1, and then we add 1. If we look at our y values, what we're doing is adding 4 each time. So negative 2 to 2 is plus 4. From 2 to 6 is plus 4, and plus 4. So our rate of change, which we write as delta y divided by delta x, is 4 divided by 1, which is 4. Let's look at the next example, and we'll quickly fill this in. So you can double check this if you want, but these should be the entries in this table. Okay, so let's look at the changes that we have here. So going from negative 3 to 0, we are adding 3, and then we're adding 3, and adding 3, and adding 3. To go from 7 to 5, now we always work down the table when we're doing this process. We're actually subtracting 2. So take 2, take 2. So this is what our change is. Our change is negative 2. Well, our rate of change, which is delta y divided by delta x, is negative 2 divided by 3, which we can't simplify that fraction, so it's negative 2/3. Now, I will give you just a moment to see if you can notice something quite important here. So if you haven't picked it up, each time this rate of change was the same as that number multiplying the x, the coefficient of x. That was what we were labeling m earlier. In fact, for a linear function, this is always going to be true. So, linear functions are functions with a constant rate of change. So this isn't true for all functions. In fact, it's kind of a defining feature of a linear function. If a function has a constant rate of change, it's linear. Now that constant rate of change is that number multiplying the x, which if you remember, we call a coefficient. So it's the coefficient of x. So when we have y equals m times x plus b, that m is equal to delta y divided by delta x. Now there's another way we can write this which will be very helpful for us in the future. The change in y is equal to m times the change in x. So if you know how much x has changed and you know the rate of change, you can multiply them to get how much y has changed. So finally, we're going to get to what this video is actually about. How do we take a table and find a rule for it? So let's have a look. In this table, we see that x is going up by 1 each time. So let's write those changes in. So from 0 to 1 is plus 1, from 1 to 2 is plus 1, and from 2 to 3 is plus 1. On the other side, we've got from 7 to 12 is plus 5, and then to 17 is plus 5, and then to 22 is plus 5. So our rate of change, which I'm going to label as m now, since we, whoops, I don't know what I was writing there. I'm going to label it as m since we know that is the rate of change. So that is delta y divided by delta x, which in this case is 5 divided by 1, which is 5. So that's actually 1/2 of the rule we want to find. That tells us that y is 5x plus our constant b, which we don't know yet. Now, to work out what that b is, what we need to do is pick one of the entries in our table. Doesn't matter which one. Though I'm going to pick this one here for reasons that hopefully in future will become clear why this is the one we want to pick. So what that really means is that when x is equal to 0, when our input is 0, our output y is 7. Taking these values, we can substitute it into our rule that we have so far. So y is 7. We've got our 5. X is 0. And then we've got our b, which we don't know yet. 5 times 0 is 0. So what this is saying is that 0 plus b is equal to 7. Well, the only way that can be true is if b is equal to 7. And that means we now have our rule. Y is equal to 5x plus 7. Now we should check that this actually makes sense for the table that we have. So let's check, let's say this entry here, 217. So 5 times our input x, 5 times 2 is 10. 10 plus 7 is indeed 17. So this rule does work for that particular entry. And hopefully if we went through and checked the rest of them, it would also work as well. Okay, let's move to the next table. So let's find our changes. It seems that we are adding 3, and then we're adding 2, and then we're adding 4. So this is going to be a little less convenient than what we did in the last table where we always had the same changes. But that's okay, this can still be a linear function. because it doesn't have to be that the changes are the same. It just needs to be that the rate of change is the same. To go from 5 to -1, we take 6. From -1 to -5, we take 4. And from -5 to -13, we take 8. Now, our rate of change is going to be change in y divided by change in x. Let's pick one of the changes. Let's pick the first one. So we've got delta x is 3 and delta y is -6. So this is -6 divided by 3, which is -2. Now hopefully you can see that we could have picked any changes that we wanted to and divided them. We still would have got -2. And in fact, that's required for this to be a linear function. Okay, so this means that y is equal to -2 times x plus our constant b that we don't know yet. Let's pick an entry in the table to use. I'm going to pick this one. We're sort of stuck using negative numbers, and it'd be nice to avoid negatives, but one's a nice small number, so that will hopefully make our calculations a bit easier. So when x equals 1, y is -5. So substituting these values into our rule, at least the amount of rule we have so far, -5 is equal to -2 times 1 plus b. Or to evaluate this multiplication here, -5 is -2 plus b. The only way that works is if b is -3. So there's our rule. Y equals -2x. Now I could write plus -3, but I'm going to write it as take 3 because that's a bit more concise. Now again, we should double check that that makes sense. So I'm going to leave that to you to check that this rule does actually work with the entries in this table. Here's our last example. So from 0 to 8, we add 8. From 8 to 12, we add 4. And from 12 to 24, we add 12. Now from 8 to 14, we add 6. From 14 to 17, we add 3. And from 17 to 26, we add 9. So our rate of change is change in y divided by change in x. I'm going to take the last entry this time. Doesn't matter which ones I use, as long as I've got the same changes, corresponding changes that I'm looking at. So delta y is 9 and delta x is 12. But you'll see that this simplifies to 3/4, or 3/4. And hopefully you can see it didn't matter which changes we chose, we would have ended up with the same changes anyway. Now, this is a fraction, clearly, but good news is that doesn't change any of our rules for how we use this. So y is 3/4 times x, or 3/4 of x, plus our constant b that we don't know yet. Now, like before, we can pick any entry in the table that we want. I'm going to pick this one. And you may have picked up, I like using x equals 0 where I can. Hopefully, you might be starting to figure out why that is. So when x equals 0, y is equal to 8, which means, substituting these into our rule, y is 8. Then we've got 3/4 times 0. And then we have b, which we haven't figured out yet. Well, 8 is equal to 3/4 times 0 is 0. So 0 plus b. The only way that works is if b equals 8. So that's all the information we need to figure out our rule. Y equals m, which is 3/4. Times x plus b, which equals 8. Let's generalize this process that we've just gone through. So to find a rule from a linear table, the first step we need to use the table to calculate the rate of change and we're going to refer to that as m. Now we're going to use our value m that we've already found and the values of x and y from one point. Using them, we're going to solve for our missing constant, b. Once we know m and b, that's all we need to write down the rule. And finally, if you have a rule, we should check that the rule actually is true for the values that we have in the table.